look at a couple things. So yeah, what is this thing up there? I don't know why I stuck that up there. I just happened to have that. When I was grabbing my stuff to make this flip chart, I just happened to have that picture. I stuck it in there. What is it? What is it, Raymond?
It's a fractal.
It's a fractal. Okay. We'll talk more about these later. What is a fractal? What's it mean to be fractal? Okay, kind of. It's infinitely repeating, but things. A fractal is a noun and an adjective. I think it might even be an adverb. Something that is fractal is something that is self-similar on different scales. Okay, so, like for example, you could say that like a mountain range has a certain degree of a fractal, because when you look at a mountain range from a distance, it looks kind of jagged. If you get closer and you look at an individual ridge, it looks kind of like just a scaled down version. And if you get even closer, a little piece of that ridge looks like a smaller, I mean, it all kind of looks the same, right? So things that do that, like tree branches, right? If you look at a tree branch from a distance, you see you see a tree branch. If you get closer, it still continues to branch. Things like that are fractal in nature. So this is a fractal. This is more than just a fractal, though. It is a fractal, but it's a member of what's called the Julius set. This is called the Mandelbrot set. Okay, the Mandelbrot set is. We'll look at this sometime when we're between some units and it's like right before a vacation or something. We'll take a day or two, and I want to introduce you to the wonders of the Julius sets and the Mandelbrot set. It's pretty cool stuff, and they have big implications in lots of things. But among other things, this is the kind of stuff that people would use to create artificial scenery in movies, for example. Right, because you can create a tremendous amount of detail with just by controlling the parameters of the Julius set. And so, like when you watch a movie like Avatar or something, right? They're creating this entire planet, and you've got landscapes that are filled with all these little trees. Well, I mean, they're not going to. What are they going to do? They're not going to somehow animate all those little trees. You're controlling some sophisticated software that manipulates fractals and repetitive sets like this, and you're saying, okay, I want them to look a little bit more conical, and then that means something mathematically. When you change those parameters in the software, it's going to change the mathematical parameters just a little bit, and it creates something that looks a little more like what you want. But it's all based on this concept. So we'll get back to that later. Interesting stuff, though. All right, so for today, though, we want to talk about derivatives of the other trig functions, right? What's the derivative of sine x? Cosine x. What's the derivative of cosine x? Negative sine x. Good. So now we want to get the other four, right? Tangent, cotangent, secant, cosecant. All right. So remember, we've got our product and quotient rules from yesterday, right? The quick review. Remember, the product rule is easy because it's a sum of two terms. It's a piece of cake. Oh, I got one for you though. Put this. Well, this will be. I know I'm a little behind on the notes, but I'll publish all the notes after school today, so make sure everything's up there. You can generalize the product rule. So, like, if we were going to do something, this doesn't show up in like first year textbooks very much, but it's good to know because this becomes something you need to use. Like if you do the derivative with respect to x of u times v times w, what do you think happens? I mean, and you can derive this for yourself. It's not a big deal. I mean, how could you do this? How could you come up with this? If I said, prove this right now, what would you do? The derivative of u times v times w. But all you have right now is a product rule for a product of two things. What could you do? Yeah, okay. I could do like for example, u times the product of v and w, right? And so when I differentiate this, I'd have the product of u times the quantity vw, right? And then when I differentiated v times w, that term, I'd have to use the product rule there again, right? So I'd have kind of a product rule within a product rule. But if you do that, the end result is you get this. You get uv w prime plus u v prime w plus pattern. Yeah. Okay. So you can do that for as many terms as you want, right? You're gonna get a term for every factor in the product. Okay. And those can be commuted because they're being added, that's no big deal, but you gotta be more careful with the quotient rule, right? Quotient rule is VU prime minus UV prime over V squared. In other words, low D high minus high D low over low squared, right? Okay. All right, so let's find the derivative of tangent. We can do this because we could write tangent in terms of the base trig function sine and cosine as a quotient and just use the quotient rule. All right, so what are we going to get?
Cosine.
Excuse me, I'm going to get low times d high, get derivative of sine, minus high all divided by good. So let's just simplify this then. So that's just going to give us cosine squared, right? What's that going to be? Okay. That looks messy, but that simplifies quite a bit. Yeah, that's, you ever get that's 1 on top? Remember, that's the Pythagorean trig identity. Okay? So I get 1 over cosine squared x equals, that's the same thing as saying 1 over cosine x quantity squared, right? And what is 1 over cosine x? Secant. So we end up with secant squared x. That's what we get when we differentiate tangent. Okay? Does that one, how familiar, how quickly did that come to mind? Be honest, because if not, I can, you didn't remember that.
No.
Zero.
Zero out of 5.
Okay, 0 out of 5. So that's a big one. So let's take a second and let's do just a build in a little trig review here, because that's an important one. So if we're doing,
We were gone for something.
Yeah.
When that happened, me and you.
She was just like, this is the
This is how you do it.
okay, so let's look at this. Of course, we're going to look at this on the unit circle, right? If we're going to take a point on the unit circle, like right here, and this is going to be some angle x, then the coordinates of that point are cosine x, sine x, right?
Yes.
Okay? And so if that's true, then that's telling me that, let me color code that. I'd have to do this to be really slick. Let's go. So that point right there. Has coordinates cosine x, comma, sine x, right? Okay, so if those are the coordinates, then doesn't that mean that that distance from there to there is just cosine x? Everybody agree? That's the meaning of those
Yeah.
coordinates.
Yeah.
So we're gonna get cosine x and sine x. Well, there's your proof, because what's unit circle? So the radius is 1. By Pythagorean theorem, then sine squared plus cosine squared equals 1, right? Okay?
That makes sense.
So there's a way, you can use the unit circle to just represent that relationship, okay? Now, the other thing that you can do with this that's really useful is there are 2 other Pythagorean relationships that I never remember. I don't want to waste those brain cells, so I just always start with this one, because this one's pretty obvious and easy to remember. And then you can come up with the other 2 by just dividing both sides by whatever you want to get. What I mean by that is, so if we want to write this in terms of tangents and secants, what would I divide both sides by? No, cosine, right? By cosine squared. Divide each side through by cosine squared. If I do that, look what I get. If I split up this fraction over here, I'm going to get sine squared over cosine squared. It's tangent squared, right? And then cosine squared over cosine squared is 1. And then over here, I get secant squared. So there's another way of writing the Pythagorean trig identity that relates tangents and secants. That's useful, okay?
Now I'm starting to understand it. Yeah, unless we did just make equations out of it.
Okay, if I want to come up with cosecants and cotangents, then I'll divide through by sine squared. Right, and then I'm going to get 1 plus cotangent squared, right? Cosine over sine equals cosecant squared x. Okay, so now you kind of slice and dice that thing however you want to in order to come up with these relationships. And when we're doing trig algebra, manipulating trig stuff, those are really useful because we a lot of times, and you'll use this. We won't really get to this year. This is going to be, it'll be pretty ambitious for us to get through. Clear to the point where we do solving integrals by the technique called trig substitution. But you'll do that next year, and it'd be like in your Calc 2 class. It'd be in 252. And then this becomes really a big deal. Then this becomes very useful for simplifying integrals, because that's even more important than simplifying derivatives before you start. I mean, that's really, I don't want to talk about that too much, because that's the second half of the year. But anyway, that's useful, okay? So going back to our problem here then, we came up with the derivative of tangent is equal to secant squared. Okay, so there's another standard form we can add to our list. Let's do derivative of secant too while we're at it. Okay, secant is just 1 over cosine. Now, we've got to use, it seems like kind of a waste to use quotient rule on that, doesn't it? Because we got a 1 on the top. But we have to for now. We have to for now. And the reason we do is because the only other way I could write this, I could put the cosine on top, but I'd have to write it as cosine x to the negative 1 power. And we don't know how to do that yet, but we will pretty soon. And then we could have done this more easily. We wouldn't have had to have done the clumsy quotient rule, but for now we do. We just don't quite have the tools in our toolkit to deal with it otherwise. That's okay though, it's not a hard one to do. So what's that going to give us? So cosine x times 0 minus
1
times all divided by cosine squared x. Okay, so we could simplify that, right? And if we simplify that, we're going to get 0 plus sine x over cosine squared x. Okay? Is there an easier way to maybe write that?
Can you split up terms so that you have sine and cosine?
Okay, yeah, what if we write this as a product of 2 factors? We could write this as, what if I wrote it as like sine x over cosine x times 1 over cosine x? Okay, well, what's that? Secant x tangent x. Okay, and you might ask, well, why? I mean, why put it that way instead of this way? Well, for one thing, because it's not a quotient. Right? We'd rather write it as something that's not a quotient, so it's a little easier to deal with. And then the other part, you'll have to take my word for it. When you're differentiating secants, it's convenient to get secants and tangents because it's, I don't know how to even articulate this, but if you just do lots of trig, you'll see that this is pretty useful. That the derivatives of the secants are related to secants and tangents. Because it ends up being easier to simplify your end result if you use this, for example, this Pythagorean identity, and you keep it in terms of secants and tangents. You'd rather minimize the number of trig species that you're dealing with at the same time. You don't want to get a whole slew of different trig functions. Then it's harder to work with. You want to try to keep them. Does that make sense? You want to write your expressions in terms of as few as possible. And secants go together naturally with tangents, just algebraically in terms of the trig. All right, so then we end up with, if we did this for all the, all four of the higher trig functions, we would get these results. So these are our trig derivatives. Now I want to show you, and you probably already see these patterns, but I'll show you a little pattern that makes it easy to keep these straight in your head. So what I do is I always break these up, the way I do this for myself, I always break these up into the derivatives of the normal trig functions and then the derivatives of the co-trig functions. Okay? And look at the comparisons we can make. The derivative of sine x is cosine x. So the derivative of cosine x flips it around, and that gives us a sine x. But notice that the derivatives of the co-trig functions all have negatives in the results. Okay, so they go together in that way. So you can make a prediction then. What's the derivative of cotangent going to be? Well, the derivative of cotangent is going to be, it's going to be the co-version of secant, cosecant squared, but negative, right? What's the derivative of cosecant going to be? Well, it's going to be the co-versions of these, but negative, right? So negative cosecant, cotangent, okay? And so really, if you know this side, you know that side too, right? Because if you just know the patterns, you know the relationships. I didn't say that very well, but you get the idea.
Yeah.
Okay. Okay, so let's look at just a couple quick, I mean, we can probably skip that. That's just going to differentiate term by term, right?
Yeah.
No big deal. Okay. Okay, let's just look at a couple examples here. And then the assignment that I gave you on this, this is kind of just more skills practice. This is just like, I mean, this is not really, we're just kind of getting prepared to do something with the calculus. So the next assignment that I built it, and I think I must not have saved it because I lost it, but I'll rebuild it. It's going to be doing the derivatives of the trig functions combined with some extra practice on quotient and product rule. Okay. So this is, I'll do as little as I think you need, but you need some practice on this. This is the stuff where to get good at calculus, you just got to do some problems. So it just starts to become second nature. All right, so what do we get here if I want to calculate the derivative?
X. X.
So we're going to get x squared times
Secant X.
good, tangent, the derivative of tangent is
Secant squared.
secant squared, good, plus
2x.
tangent x times 2x, and that's it, right? That's our answer. And we could do things with that if we wanted to, but at this point we don't know what we're doing. So we would just, how would we write that though most conveniently? What are our conventions for this? Well, you want to put variables before functions. So we put the x squared before the secant squared x. Why does that make sense, by the way?
So then you don't get your x's mixed up.
Yeah, right. You don't confuse yourself by saying, okay, is that an argument of the secant, or if it's out front, then it's unambiguous, right?
Yeah.
How should I write this one?
2x.
You have constants first, numeric constants first, then symbolic constants, then variables, then functions. Okay? And just kind of the way it should be. Okay, so what do you suppose these things mean?
We're going to
take the derivative.
Derivative of the derivative.
Okay, yeah, good. So we'd say, we call this the derivative. Really, it's the first derivative. But we get lazy. If we say derivative, it implies first derivative. What's that?
Second derivative.
Second derivative.
Third.
Third derivative,
Fourth.
fourth derivative, and so on, right? And each one of those is just a derivative of the preceding derivative, right? So we end up with, what's this gonna be?
20x to the fourth
Plus
12x to the third minus 4x plus 10.
Okay,
80x to the third
plus
36x squared.
minus 4.
Oh.
240x squared plus 72x
and finally,
480x plus 72.
okay, so I mean, why did I have you do that? I mean, just get a little practice, I suppose, but what do you notice when you take a polynomial and you differentiate, what happens to it?
It's
It
more
gets smaller.
It gets smaller, it's simpler, doesn't it? Right? Okay. All right.
It's just 72.
Okay, let's look at something a little different, a little more useful.
It's x to the 75th.
The derivative of secant is no big deal, right? Derivative of secant is no big deal, but you'll start to see that sometimes when it doesn't always work this way like it did with polynomials. Are so nice. They're so well behaved and so nice. A lot of other functions don't work that way. Polynomials always get easier when you do successive higher derivatives. A lot of times other stuff doesn't. Okay, let's look at an example. So what's the derivative of secant?
Secant x tangent.
Okay, now what? Okay, how am I gonna differentiate that?
Product.
Product, right. So I got first times derivative of the second plus times
Secant x tangent x.
and second times derivative of the first, okay? And that's a little bit of a mess right now, and that's just gonna get worse and worse, isn't it? We could clean this up a little bit though. If we clean up each individual term, I'm just gonna get secant cubed plus
Tangent squared.
secant x tangent squared x. Okay, so what could I do to maybe clean this up a little bit? I could take a secant out, right? I could factor a secant out. And if I do that, I'm left with secant squared x plus tangent squared x. Okay. Now, for reasons that are going to be mysterious to you at the moment, what if I said we really want to write this in terms of just one trig function? Which one would we want to put this in terms of? Secant. And how could we do it? There's got secants and tangents go together, right? Yeah, there's a Pythagorean rule for that. What is it? I never remember. I always just do this. Sine squared x plus cosine squared x equals 1. So if I divide each side of that by cosine squared, I'm going to get tangent squared plus 1 equals secant squared, right? So tangent squared must be secant squared minus 1.
Yes.
Okay? So then I could write this as secant x times secant squared x plus, see it was,
Secant x squared minus.
there we go. And so now if I were to kind of recombine stuff here, I'm just going to get secant squared plus secant squared is 2 secant squared times secant, 2 secant cubed, and then minus secant x. Okay. That's not going to mean a lot to you now, but later in your calc careers, that'll mean a little more to you. Okay, that'll be useful to do when you're solving some later trig equations. So I just wanted to reinforce for a second, why did I talk about the Pythagorean trig identities? There's an example.
I don't see very many numbers.
No, you'll see fewer and fewer numbers as we go forward. Okay, let's just do maybe one more, just to get a little practice with kind of a harder one. And then I think it's time to just work on this stuff and just get some practice. Okay. So y prime.
3 plus 3, so
Oh, good. Times.
Times 8 secant squared x.
minus 8 tan t times
Times
D low. Now what's D low here? What's the derivative of 3?
0.
0.
And then 3 times secant x tangent x.
Okay, good. So I get 3, derivative of 3 secant t is just 3 times the derivative of secant t. So we get 3 times secant times tangent, all divided by
x vector plus 3 secant t's.
quantity squared.
Yes.
Okay. So what could we do here? It's a kind of a mess, isn't it?
Yes.
So it's a real mess. So we could factor out an 8 times a 3,
Yeah.
right? Everybody see that?
Yeah.
So if we factor out, if I factor this 3 out, and I factor that 8 out of this term, I can take a 24 out of the first term up here, and a 24 out of the second term, right? And then what am I left with? So then I'm left with,
1 plus secant.
and I'm gonna go ahead and combine stuff here, right? If I distribute that secant squared, I'm gonna get a
1 plus secant cubed.
1 plus secant times secant squared is gonna be secant squared plus secant cubed. Am I skipping too many steps?
I'm lost.
Okay, I'm skipping too many steps. Let me go back a step here. So let's do this. Let's go on the top. Let's go ahead and factor a 3 out of this.
Yeah. 1 secant.
T.
Okay. Let's take an 8 out of this. And that's leaving us with
Secant squared.
secant squared t
But
minus, let's take a 3 and an 8 out of these two.
tan t.
Wouldn't the secant squared t be divided by 3 if you took?
No, because the 3's out front.
No, because I'm factoring a 3 out of this, right? So would you agree that this
Oh,
whole thing
okay,
right here
okay,
is just
okay,
that,
yeah, yeah,
and this whole thing is just that, because
Okay.
we multiply it?
I get it.
Times, what's left over then? Well, then we've got a
Tan t.
tangent t times
Secant t.
secant t
And then secant t.
tangent t, right?
Yes.
And so now, how many terms are there in the top expression there? 2. I get this big term minus that big term, right?
Yes.
Yeah.
Yeah. See what I mean? Now, there are terms within the factors, but that's not what I'm asking. I'm asking how many terms are there, how many broad terms are there in that top expression? 2, right? So 2, and this is a big complicated one. And this is a big complicated one with lots of factors, right?
Yep.
Okay, and then the bottom just stays the same. So now we could factor out this 24 out of these 2 terms.
Yes.
And so we're going to get 24 times this stuff, right?
Yeah.
So if I distribute there, I'm going to get,
Secant squared
Plus
plus
secant
secant
cubed.
cubed.
good,
Minus.
okay, I'll go ahead and put parentheses around that, minus, just so we can track that minus sign, there it is.
Tangent
And
squared.
then over here, I just get my,
Secant.
yeah, tangent squared times secant. We good?
Yeah.
That make sense? Okay. Then bottom just stays the same. T right, so what do I probably want to do here?
Secant and secant.
I could factor a secant out of both, that's a good idea. Okay,
Sure.
could do that. I can do that. Do I,
Well, you could change the tangent to secant.
okay. You see that? What's the red flag on top? You know, what's the, everything looks pretty uniform, except I've got this tangent up here, right? If I want to be able to combine like terms here, do you see the motivation for that too? And it's doing math, I mean, it's kind of like playing chess or something. You gotta really, you're sort of thinking ahead.
Just dancing around.
We want to be able to, in order to simplify this expression, I really want to be able to combine as much of this on the top as possible, because it's messy right now. The only way I'm going to be able to combine like terms here is if I get just powers of secant that go together, right, that match. And so I want to convert those tangents into secants, but tangent squared into secants. That was just secant squared minus 1, right?
Yes.
Okay, so we could, we could write this then, next step. I've got my 24 out front. I've got my, I don't need those parentheses. Secant squared t plus secant cubed t minus secant t times secant squared t minus 1. That's looking better, right? Okay, and then finally, no, I'm going to the next page. This happens a lot in calculus. We'll go through, I'll have to like cut, go to the top of the next page, and just happens a lot. Okay, that's where we left off, right?
Okay, so now we go on to distribute.
So if I distribute here,
You get secant cubed, which makes it secant cubed.
minus
Secant cubed.
secant cubed plus
Secant.
secant cubed, good. Good. All over.
All over here. Same thing.
Okay, and so, getting tired of it. Double tunnel up here. So the secant cubes cancel,
Needs a rest
And
break.
you want to factor out secant.
and I can factor out a secant, okay? And then now, look what we're getting.
And you
Then I've got
factor out
24
this.
times
Secant.
secant t times. If I factor one out, then I've just got secant plus 1, right?
Yeah. It's
Try
good.
to do something else.
Divided by okay, it's pretty good. Now stare at that. Is there a way we could do something else there? What else? Wouldn't it be nice to be able to cancel some factors here also? That's always good.
Read out to the bottom.
Okay, so we got two possibilities here. Now, and you gotta be very careful with this, right? So the question is, can we factor a 3 out of the bottom? And the answer is yes, but we gotta be careful, right? If I factor a 3 out of the bottom, am I actually factoring a 3 out of the bottom?
You factor in 3
We're
squared.
factoring a 3 squared. So if I were to do that, and we're gonna make a little sidebar here, where this is separate issue, that bottom there. If I wanna simplify 3 plus 3 secant t squared, that's really equal to 3 times the quantity 1 plus secant t all squared, right?
Yeah.
So inside the squared, I factored a 3 out. But we have a property. You remember this property from algebra 2. If I have a times b to the n, that's equal to a to the n times
Oh,
b
yeah.
to the n, right?
Yeah.
Okay, so we can apply that here, and then that would just become 3 squared times 1 plus secant t squared, right?
Yeah.
Okay, that's fine, we can do that. And then we could cancel the 1 plus secant t and have a 9 on the bottom. The other thing we could do if we wanted to, is we could maybe just, say
Yeah,
again,
you'd still have a one
It's
plus
the- on the
CPNT.
bottom.
you'd have a 1 plus CPT on the bottom, right? Only
Yeah.
cancel one of the powers, right?
Yeah.
The other thing you could do is you could maybe also just break this into an 8 times a 3 and just multiply 3 up here and cancel one of them that way. But then you still have a 3 stuck in the bottom,
Mhm.
right? They're both fully legitimate ways to go with this. They'd be fine. They'd both be fine.
This is
And
only
so
the
that's the
first derivative.
Yeah, so either one of those would be the answer. Let's, just so you see it another way, what if we did this? What if I broke this 24 up? So we had an 8 secant t times 3 secant t plus 3 divided by 3 plus 3 secant t squared. And then look, we get, then that cancels with one of those, right?
Yeah.
And so we end up with 8 green stuff. Okay, so we get something pretty concise, but that's a lot of work.
How many problems like that do we have?
I gave you one pretty good one like that. I'm going to give you one pretty good one like that.
I'm good with one. Maybe. We'll probably come at different.
Okay, does that make sense?
Yeah.
I won't be here Monday or Tuesday.
Same here.
Yeah.
Walk you.
Okay, so I will, what are we at here, 25?
Yeah.
Okay. I'd be willing to maybe give you, Monday's a short day anyway, I'd be willing to give you Monday a day to kind of work on